Let's go over one more example where we're going to use a trick that you may have to use another time. Let's say we want to calculate the integral of e to the x sine x. Doesn't look like there's a easy substitution, and so well, if we don't know what to do, we can always try integration by parts. Since we have a new toy, right, a new technique to calculate integrals, we can try and see what we get, with no guarantee, of course, that it would work. Now, to start with, we have a little bit of a problem to choose what is going to be u, what is going to be dv. Recall that our integration by parts formula here is under the form integral of u dv is uv minus integral of v du. So we have to pick what is going to play the role of u and will be differentiated, and what will be playing the role of dv and will be integrated. Yeah, it's not clear what to pick because both e to the x and sine x, when we differentiate or integrate, we get essentially the same complexity. Well, so let's pick something. Let's take sine x for u and e to the x dx for dv. Then du is cosine x dx, and v is an antiderivative of e to the x, so just e to the x. We apply our formula, and our integral rewrites as uv, that's e to the x sine x, minus integral of v du, that's integral of e to the x cosine x. Okay, it looks like we didn't gain a lot because we started from this integral of e to the x sine x, and transformed into integral of e to the x cosine x, which evidently has essentially the same type of complexity. So we didn't really simplify anything. We transform this integral of e to the x sine x into integral of e to the x cosine x. Okay, so what can we do next? Well, if integration by parts on e to the x sine x gave us the integral of e to the x cosine x, maybe integration by parts on the second integral will take us back to integral of e to the x sine x. And in that case, we will have this integral of e to the x sine x on both sides, and maybe we can solve. Well, that's worth a try. So let's use integration by parts on this integral. And let's say we take u is cosine x and dv is e to the x dx. Then du is negative sine x dx and v is e to the x. If we use the integration by parts formula, we obtain that the integral of e to the x sine x is, well, this e to the x sine x minus, and then we replace this integral using integration by parts formula, so we get uv, e to the x cosine x, minus the integral of v du, but du is negative sine x dx, so minus integral of v du is going to give me plus integral of e to the x sine x. And now I have this negative sign in front of a parenthesis, so I have e to the x sine x minus e to the x cosine x, which I can write e to the x multiplied by sine x minus cosine x, and then I subtract this integral of e to the x sine x. So this is what I have. And here you see that we have the same integral on both sides. So we can solve for this integral. Namely, here I could, for instance, add integral of e to the x sine x dx on both sides, and then what I obtain is 2 integral of e to the x sine x is equal to the explicit function e to the x multiplied by sine x minus cosine x. Dividing both sides by 2, I obtain the integral I was looking for. Of course, this is up to a constant, because here we are just writing an antiderivative of the function e to the x sine x. So here this trick of using integration by parts twice in order to obtain an integral in terms of itself and then solve for it is something that you may have to use in other problems as well. Now that we've seen pretty much the standard situations to use integration by parts, it's time for homework.